Good afternoon. My name is Michael Paya. I'm in third year of PhD under the supervision of Olivier Pouliken and Maxime Nicolas, and I'm talking about the initiation of submarine granular avalanches. First, our work was motivated by a large-scale experiment from Iverson. It's two experiments, a dense soil and a simple soil, and they add water, and the avalanche starts. For the dense sample, the soil, the granular material just creeps, whereas for the loose sample, we'll see that the dynamic is very different. Yeah, it rapidly starts, and it's catastrophic. Yeah. So, a pore pressure feedback argument in order to understand what's happened. If we start with a loose case. When beds flow, they will compact, so fluid between beds will be expelled with an increasing of the fluid pressure, so granular pressure decrease, friction decrease. There is less friction between beds, and it's flow easily. Whereas in the dense case, to flow, beds have to dilate, so fluid between grains is sucked, fluid pressure decrease, granular pressure increase, so friction increase, and it's more difficult to flow. So we try to reproduce that at a small scale, and the little experiment, it's just a bottle full of water and glass bead. We put a grain in a suspension, we let it deposit, and it's the loosest case we can obtain. And then for the dense sample, we tap 3 times. The loose sample immediately starts, whereas it seems that nothing happened for the dense sample, and then the avalanche is triggered. So here is our experimental setup: a long box, 1 meter long, full of fluid and a layer of glass bead. We measure the free surface velocity with a camera, also the free surface position, the thickness of the layer, with a laser at a low incidence angle, and also the pore pressure with a pressure sensor. The pore pressure is the pressure of fluid between beds, and it's taken below the layer. The procedure of the experiment: so we mix, like in the case of the bottle, we mix and we put a grain in suspension, we let it deposit. The result of sedimentation is the loosest case, and we can control the compaction by tapping on the box. Then we suddenly incline the box at a chosen angle. 2 fronts develop at the extremities, and in the central part of the box, the triggering, the flow, is uniform, and in this area we measure velocity, free surface position, and pore pressure. Here is typical result we obtain. Here is represented the time evolution of the velocity and of the pore pressure for different initial volume fraction. The red curve is the loosest case, high compact, and then the black curve is the densest case. The first observation is that the final state for the velocity seems to be the same it's the steady state velocity. And we can class this in two categories, loose and dense cases. For the loose cases immediately start with a strong acceleration, and then the velocity goes to the steady state velocity. And for the dense case, the avalanche is delayed, and the more we increase the initial volume fraction, the more the avalanche is delayed. We have first a slow dynamic, and a triggering time appeared. And once the avalanche is triggered, we obtain the same dynamic. For the pore pressure, we measure a negative pore pressure in dense case and positive pore pressure in loose case, something like that. And now we are looking at the triggering time in the dense case. It's the time it takes to the avalanche to start. The triggering time as a function of the initial volume fraction. So it increases with the initial volume fraction, but it also depends on the angle and on the thickness of the layer. Here we will see that the important parameter is the deformation. First, I've plotted the velocity as a function of the time, and then I've plotted the surface velocity not as a function of the time, but as a function of the deformation, like defined here. And the three curves collapse, and we obtain that the avalanche starts for a deformation around 0.25. So for a deformation of 0.25, the avalanche is triggered. The initial preparation is erased. We have forgotten what's happened before, and we obtain the same dynamic for the velocity. By assuming that a constant velocity during the creeping phase and introducing this velocity u, we obtain an expression for the triggering time. So we can to estimate this velocity during the creeping phase with a very simple model, just a force balance between the gravity and the force of friction. So the force of friction is the coefficient of friction time the contact normal stress, the granular pressure, which is reduced by the pore pressure. For the pore pressure, we assume a Darcy law with vertical velocity due to the dilatancy. So we estimate this velocity here. In fact, the angle of dilatancy is the angle at the contact of two beads. And we also introduce a critical state here, which is the difference, and so the separation between the loose and the dense case with this relation for the tangent of the angle of dilatancy. By putting all that together, we obtain an estimation for the velocity during the creeping phase. So we also obtain a relation, an expression for the triggering time. Here is the data I've shown before. And now if I plot these data in terms of adimensional time with T0 that appear in the expression of T trig, we obtain that data collapse. And if we plot also the theory, T trig, we obtain a good agreement between the theory and the experiment. In this data, we have a different viscosity and also a different thickness. So in conclusion, we have shown a very different behavior between the dense and the loose cases. Triggering of submarine avalanche is delayed when compacted. The more we compact, the more the avalanche is delayed, and we can also predict this triggering time. It remains open question: what's happened inside the layer? We try to make an experiment using index matching method, and what's happened also toward a non-uniform flow. Thank you for your attention.
Questions? Yes.
How do you measure the pore pressure?
Just with a pressure sensor and with a pressure hose under the layer, and
Is in direct contact with the medium, or there is some support?
I don't understand.
Is the sensor in direct contact with the medium? Is it embedded in the medium, or is it below the plane of?
No, it's we needn't to be in contact directly. The signal spanned through the hose. And,
So it's an invasive method.
Something like a mouse.
It's an invasive method. No, it's on the bottom surface.
Any other questions? Yes.
How do you measure your compaction or your volume fraction?
From the thickness with the laser at low incidence angle, I measure the thickness, and I can so measure the volume fraction.
If there are no more questions,